Assalamualaikum and hi. My name is Siti Damia, metric number 22134. So I will be talking about heart disease prediction using age and resting blood pressure, which is K nearest neighbors approach. As we all know, heart disease is a major global health issue, contributing to about 70.9 million deaths annually, according to the World Health Organization in 2021. However, many cases of heart disease are preventable through lifestyle changes and early detection of risk factors like smoking, poor diet, obesity, physical inactivity, and more. Early detection plays a critical role in improving patient prognosis and reducing healthcare costs. The primary objective of this experiment is to develop a model that can predict the presence or absence of heart disease based on two selected features, which are age and resting blood pressure. This is achieved by applying the KNN algorithm to a comprehensive data set that includes multiple health-related attributes with a specific focus on clinical and demographic data. This report is organized into several sections to provide a clear analysis of using machine learning to predict heart disease. The background of the dataset section explains the structure and features of the dataset, including the clinical and demographic data. The methodology section describes the K nearest neighbors algorithm and the steps taken for pre-processing, training, and testing the model. In the result and discussing section, the model's performance is shown, including its accuracy and a decision boundary visualization.
Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nabila Radia binti Ahmad Rizwan and my metric number is 2213554. And I will be explaining on our dataset, which is the heart disease prediction dataset. We got this dataset from the website Kregel, and the reason for why we chose this dataset is because it is useful in analyzing and predicting cardiovascular health outcomes by using data analysis and machine learning. This dataset also includes a diverse range of clinical and demographic data, which enables the in-depth evaluation of heart disease risk. And lastly, it offers insights into potential health risks and assists healthcare professionals in making informed decisions for their patients. Next is the dataset attributes. In this heart disease prediction dataset, it provides a few attributes that can be categorized into demographics, clinical, symptomatic, electrocardiographic, genetic, and outcome variable. This group project used around approximately 1,700 patient records, and if you dive into the attributes that was given in this dataset, firstly is the demographic, which is the age and gender of the patients. And then secondly, it is the clinical attributes. In the clinical attributes, there are resting blood pressure, which is measured in mmHg. And then it has serum cholesterol, which is the cholesterol level in the blood measured in mgdl. And lastly is the fasting blood sugar, which is an indicator for blood sugar levels above 120 mgdl. And then next is the symptomatic attributes. It has chest pain type, which is the type of chest pain that was experienced by the patient. And then secondly, it is the exercise-induced angina, which is an indicator for the presence of angina induced by exercise. And next is the electrocardiographic attribute. Firstly, it has resting ECG result, which is the data for the electrocardiographic result. There are three types, which is normal, STT with abnormality, and then left ventricular hypertrophy. Then next, it has maximum heart rate achieved, which is measured in beats per minute. And this dataset also includes ST depression, which is depression in the ST segment induced by exercise relative to rest. Next is the genetic, which is thalassemia, an indicator of the thalassemia type that the patient has, which is that categorized into three: normal, fixed defect, and reversible defect. Lastly is the outcome variable, which is the likelihood of the patient to get heart disease. And that's all for the dataset attributes.
Hello and Assalamualaikum everyone. My name is N.Fatihah Hamzah, metric number 2210378. For the algorithm, I'll be walking you through the K nearest neighbors KNN algorithm and how it can be used to predict heart disease based on age and resting blood pressure or BP. We will also dive into a decision boundary plot to help you understand how KNN classifies new data points. The decision boundary plot shows how KNN separates that data into two classes, heart disease or no heart disease, based on the proximity of points in the feature space, age, and BP. There are two key elements, which is the shaded regions, where represent areas predicted as one class, such as heart disease or no heart disease, and the second one is boundary lines, indicate where the model changes its prediction, showing how the algorithm distinguishes between classes. There are two data representations. Firstly is the dots represent the training data points color coded by their actual class, and the second one is irregular boundaries, which is highlight KNN's adaptability to complex non-linear relationships in the data. This plot showcases KNN's strength in capturing patterns based on feature proximity, the irregular boundaries reflect the parameter k, which is set to 5, and possible noise in the dataset. This makes KNN a versatile tool for nonlinear classification tasks. So after this, we will go on to the coding walkthrough video where I will be explaining more details on what implementation that we have used the to plot our analysis based on age and resting blood pressure. Hello again everyone, welcome to our coding walkthrough video. So firstly, I will briefly explain about K nearest neighbors or KNN, the algorithm that we choose for our group project. This algorithm classifies data based on the proximity to other data points. Imagine you want to know if someone has heart disease. The algorithm looks at the closest data points to this person and makes a prediction based on their similarity. It's like asking your neighbors for advice, for instance. So in our coding, in our dataset, we have two important features, age and resting blood pressure. Both of these are categorized into groups to make the analysis easier and more intuitive. So as for the resting BP, it's categorized into 5 groups: low BP, normal BP, elevated BP, hypertension stage 1, and hypertension stage 2. Each of this group is mapped to a number, to a number 0 for low BP, 1 for normal BP, 2 for elevated BP, 3 for hypertension stage 1, and 4 is for hypertension stage 2. Same goes to the age. Age is categorized into 4 groups: young adult, middle age, older adult, and senior. So similarly, these categories are mapped to number 0 for young adult, 1 middle age, 2 for older adult, and 3 for senior. By categorizing age and resting BP, blood pressure, we make it easier to visualize and classify data points. Now, you might be wondering about the negative numbers. So these typically come from a process called standardization. In machine learning, when we scale the features, we often transform the data so that it has a mean of 0 and standard deviation of 1. This process is useful because it makes sure that all features are on the same scale, especially when we are using distance-based algorithms like KNN. In the case of standardization, data points below the mean will have negative values. For example, if someone's age or resting BP is lower than average, as you can see here, and there's a lot of others that below, if we want to divide it, it's like here until here, until the before 0. So, for example, if someone age or resting BP is lower than the average of the data sets, their transform value will be negative. This doesn't indicate any error or problem. It is simply a result of the mathematical transformation and is totally normal when using algorithms like KNN. As for the shaded areas on the plot, it represents regions where KNN predicts a certain class. For example, one area might predict no heart disease and another might predict heart disease. These regions are created by the KNN classifier based on the proximity to other points. So as we always know, blue means good and red means dangerous zone. As for the color of the data points, which is the dots, I'm sorry, for the dots color, blue represent individuals without the heart disease and red dots represent individuals with heart disease. So what does it mean if someone with heart disease but on this blue zone? So this means that this person is not in a dangerous state yet. So as we can see, this person that have a heart disease and staying at the red zone, meaning that it's dangerous for them, like the heart disease state for this person is bad. And for instance, if the blue one to be in the red zone, so the blue one indicate without someone without the heart disease, right? So which mean if they are in the red zone, meaning that they have the possibility to get the heart disease. That's why they are in the red zone instead. So these colors, actually all the colors, help us visualize how KNN classifies data based on age and resting BP, of course. To sum up, KNN is a simple but powerful algorithm that can predict whether someone has heart disease based on age and resting blood pressure in this case. By categorizing these features, we can easily visualize how the model works and make predictions that are both accurate and interpretable. That's all from me. I will pass to the next presenter. Thank you.
Assalamualaikum and hi everyone. My name is Putri Anis and now I am going to explain about experimental setup. For the experiment, the objective is to predict the presence of heart disease by using K nearest neighbors with two type of features, which age and resting blood pressure. So in this experimental setup, there are three types of it. The first one is model training. For model training, it consists of data processing, and this data processing got for attributes which are data set, encoding features and target variable. For the data set, uh, a data set, a clean data set containing half attributes of patients. For encoding, the attributes is to map to numeric values, and for features, it is select for 2D visualization. And the fourth one, which target variable, it is to indicate the presence or absence of heart disease. For the data splitting, it consists of training and testing. The training set consists of 70% and for the testing is 30%. And the third one is feature scaling. It is to normalize the features for effective KNN distance calculation. And the fourth one is KNN classifier training, which to define KNN model with K equal to 5. The second one in this experimental setup is decision boundary visualization and test set evaluation. For decision boundary visualization, we created a mesh grid, a 2D mesh grid to visualize the decision boundaries. And for the test set evaluation, we use the scale data for prediction and we compare the predicted labels with true labels. And the last one for evaluation, we evaluate the model's performance using the test data, and then we visualize the decision boundary and training data points. For the accuracy, we measure the overall correctness of predictions on the test set. And the last one for error analysis, we examine the misclassified data points in the test set, and we also check the underfitting, that is pure decision boundary. I think that's all from me, and I will pass this presentation to the next person. Thank you.
In this project, we use the K nearest neighbors KNN algorithm to predict heart disease based on clinical features like age and resting blood pressure. The model effectively classified individuals into at-risk and not at-risk category, providing valuable insight for healthcare. Key findings include the importance of data pre-processing, particularly feature standardization for accurate distance calculation and feature selection, which improve the model's performance. The decision boundary visualization helps us understand how the model differentiates between risk category. For future work, we aim to expand the dataset with more features, explore algorithms like decision trees, and support vector machines that can enhance model robustness through cross-validation and integrate real-time data to make the model more applicable in healthcare environment. So that's all from our group. Thank you so much.